This is Reigate College Maths Year 2, Pure 6, Numerical Methods, and we're covering the Newton-Raphson method. So the Newton-Raphson method is a way of getting an iterative formula. You're given this formula in the formula book, and the formula is based on using the gradient of the graph to find an improved estimate. Let's just have a quick look at the textbook because there's a good diagram in there. There's the Newton-Raphson formula, and there's a diagram showing where it comes from. It's on page 282 of the textbook. I'm not going to try and replicate that myself. If you go 2 pages on, there is also a link here, this one, where you can open it up. It runs within the browser, and you can use GeoGebra to look at how this works. So we've got a root here. Our first estimate, I think, for this one is going to be 1.7. And this shows how Newton-Raphson gives us a better formula. So here's our first estimate, 1.7. Here's f of 1.7. We use the gradient of the graph. We draw the tangent at that point, and then where it crosses the x-axis, this gives us an improved estimate for the root. You can see the second iteration here as well. It gets close to the root very quickly for this one. So let's go back to the examples in the course workbook. It is useful to see where that formula comes from, but generally you're going to need to use this formula. So the formula is xn plus 1 is equal to xn minus f of xn over f dashed of xn. So for our example here, we're trying to find a root of the equation x cubed plus 10x squared minus 73 equals 0. So I'm going to define f of x is equal to x cubed plus 10x squared minus 73. I'm also going to find f dashed of x, so I'm going to differentiate. So f dashed of x is equal to 3x squared plus 20x. Not sure why I'm using a red pen. Let's use a black pen. So then we're going to use an initial value of x equals 2. So we're going to say, actually let's write out the formula. So x n plus 1 is going to be equal to x n minus, we want f of xn, so that's xn cubed plus 10 xn squared minus 73 over 3xn squared plus 20xn. So if x1 is equal to 2, then x2 is equal to, well, we've got xn there, so 2 minus 2 cubed plus 10 times 2 squared minus 73. That all divided by 3 times 2 squared plus 20 times 2. And if you work that out on your calculator, you will get 129 over 52, which is 2.48077. You can again do all that on your calculator. So let's see how we can put all of that into the calculator. What I'm going to do is I'm going to say I'm going to start with my first estimate, so that was 2, wasn't it? And we're going to press equals, and then we're going to say we want answer, so that's our xn, minus, and then let's put all this in as a fraction. We want answer cubed plus 2 times answer squared minus 73 divided by 3 times answer squared plus 20 times answer, and if I put that in right, I should get 129 over 52, which I'm not getting. So what have I done wrong? Answer squared plus 20 times answer. That should have been. So I'm going to go back up and put in my 2 again. Back up. Oops. Let's go back to here. So that should have been a 10 up at the top there, shouldn't it? Let me get rid of that. Let's go delete, and let's put it in the wrong place. Delete, that should have been 10, 1, 0 equals. Okay, so there's my 129 over 52 that I gave you earlier on. You have got to be very careful putting these formulas into the calculator, as I've just demonstrated. But now what we can do is we can just press equals again, and we get our next value. Let's see if that's what I was expecting. Yes, it is. So I have worked these out before. x3 is equal to 2.42481. x4, x5, let's find those. So we're just going to click equals again. 2.42399. Click equals again. 399048. What do we get? 2.4239903. 2.42399. We want our answer to 3 decimal places, so we can see that if we round to 3 decimal places, this is going to be 2.424, 2.424. So we can say approximation x equals 2.4243 decimal places. We can get our answer as accurate as we really want to. It just might take a bit more time if we have lots of decimal places to find. Okay, that's it for a demonstration of how to use the Newton-Raphson method. I strongly recommend writing out the formula, writing out the function and its derivative,